Now, in addition to the branch instructions, we also have compare instructions. So the MIPS architecture defines compare instructions. These are set less than. So we have 4 set less than instructions: set less than unsigned, we have set less than immediate, and we have set less than immediate unsigned. So notice that the first 2 here, we compare 2 registers, RS with RT. This is set less than and set less than unsigned. They are of the R format, okay, the R type. So we are comparing 2 source registers, RS and RT. The result is either true or false. So if the result is true, we write 1 into RD. And if the result is false, we write 0 into RD. Okay? So we have here 2 compare instructions, set less than and set less than unsigned, that will compare 2 registers, RS and RT. If the result is either true or false, so true here is 1 and false is 0. Now, the difference between set less than and set less than unsigned is that set less than does signed comparison, whereas set less than unsigned does unsigned comparison. Okay, so this is the major difference between these 2 instructions. And the comparison is different between signed and unsigned. In the case of you would like to compare with an immediate, there is set less than immediate and set less than immediate unsigned. So we're going to compare RS, source register RS, with an immediate, and the result will be written into RT. So these 2 instructions are of the immediate type because the instruction contains an immediate. Again, the result can be true or false. True is 1, false is 0. And this is written into register RT, not RD, because these 2 instructions are of the immediate type. Now, signed versus unsigned comparisons compute different results. I have an example here. Suppose that we have register T0, which is 1, and register T1 is -1. Now, -1 will be all ones in binary. So in hexadecimal, it will be all F. So the value -1 in the 2's complement representation. Remember -1, how do we represent it in binary and the 2's complement representation? It will be all ones. All ones, yes, all ones. So in hexadecimal, you can actually just say it's actually all F. Okay, 0xFFF. Okay, this is the value -1. Now, if I use sign comparison, set less than is 1. I would like to compare T0 with T1. And suppose that the value of T0 is 1 and the value of T1 is -1. So is 1 less than -1? It's false, right? 1 is greater than -1. It's not less than. So therefore, we get the result of this comparison is false. So this instruction is going to write 0 in T2 because the result of this comparison is false. So set less than is going to compare the value of T0 and T1, and if the result is false, we're going to write 0 in T2. So the result here is written into register T2. Now, in the case of set less than unsigned, is going to treat T1 here, T0 and T1 to be both unsigned. Now, T0 is equal to 1, but T1 is equal to this number here in hexadecimal. Now, this number is a huge number. Okay, it's more than 4 billion something. So when you look at it in decimal, this number will be more than 4 billion. Now, this number is not -1 because we are looking at the numbers here to be unsigned. So we're using set less than unsigned. So this instruction is going to treat this number to be unsigned. So the question is 1 less than 4 billion? Okay. This is a huge number here. The answer is true. So therefore, it's going to write 1 into T2. So you can see that here it's going to write a different result into T2. So what we have seen so far, we have seen the branch and the jump instructions. But in addition to these instructions, we also have compare instructions. Compare instructions are ALU instructions. And they compute a result. The result of a compare instruction is either true or false. True is 1 and false is 0. And the result of a compare instruction is written into a destination register, which can be either RD or RT. Compare instructions can be of the R type, the register type. Okay, these instructions write the result into RD. They can also be of the immediate type, and they write the result into RT. Okay. Now, notice that we also have compare instructions for signed integers. We also have compare instructions for unsigned integers. And these produce different results. So in the MIPS architecture, these are called set less than. Set less than is used for signed integers. It's going to compare if RS is less than RT. The result is written into RD. And we have set less than unsigned. So the difference between set less than and set less than unsigned is that set less than is going to compare signed integers, whereas set less than unsigned is going to compare unsigned integers. In the next slide, I have a list, the list of instructions, which is shown in this table. Notice that set less than and set less than unsigned, they are of the R format, the register format. And notice that the opcode is equal to 0. The function code is unique, uniquely defines these two instructions. There are 3 register fields, RS, RT, RD. So these instructions compare RS with RT and write the result into RD. Whereas set less than immediate and set less than immediate unsigned, so the U here means unsigned, they have unique opcodes. Each instruction has a unique opcode. They compare register RS against the 16-bit immediate, which is signed. And these two instructions write their result to RT. So RT is my destination for set less than immediate and set less than immediate unsigned. Now notice that the only compare instructions are less than. Okay, so we can actually have less than unsigned, less than with an immediate, and less than with an immediate unsigned. But there is no set if equal, set not equal. These instructions are not provided by the MIPS architecture. Although these are really useful compare instructions, but they are not defined in the MIPS architecture. So the assembler defines these as a pseudo instructions. So set if equal, set not equal, these are defined as pseudo instructions. Set the greater than unsigned, and so on. All of these are defined as pseudo instructions. So you can use them in programming, but they are not defined in the hardware, in the architecture. So there is no implementation for them. But what the assembler will do is going to translate these pseudo instructions into equivalent MIPS basic instructions. So for example, how do we translate set the greater than? How do we compare for set the greater than? If I would like to check that T0 is greater than T1. Anyone would like to answer this question? What will be the equivalent? Yes, تفضل Khalid.
I will put T1 first. يعني set less than T1. Sorry, the destination T2.
Yeah, destination will remain T2, yes. So we write the set less than T2, comma.
RS is T1.
Yes.
And RT is T0.
Excellent. So we switch the order of T0 and T1. So it becomes set less than T2, comma T1, T0. Excellent. So you see that small trick here, by changing the order of the registers, we can do set the greater than without the need to define this as an additional instruction, okay, in the hardware. Okay, so it can be solved by software. So the assembler can solve this problem without the need to introduce this extra instruction. This is really the idea of pseudo instructions. So pseudo instructions allow the programmer to extend the instruction set without the need to define these in the hardware. Okay, so these are not really real instructions. They are only defined by the assembler, and the assembler basically it will translate them. It is just software that will translate them into equivalent MIPS instructions. Right. How about set if equal? If I would like to check for equality, if T0 is equal to T1, how do I do this? Now, set less than cannot really check for equality, right? So I need another idea. So how do you check for equality if you would like to check if T0 is equal to T1? Anyone? This can be as an exam, for example, in a quiz or exam. Okay, so given this pseudo instruction, tell me, okay, how, okay, the assembler might translate this pseudo instruction into an equivalent. Yes, Khalid.
I'll use يعني SLT twice to check if it is greater than or less than. If the return value in both statements is 0, يعني I will add m. If I get 0, then it is equal.
So basically, if T0 is not less than T1 and T1 is not less than T0, then they must be equal. This is what you are saying,
yes.
Khalid.
Yeah.
But that's actually might require many instructions, right? Because you have to do set less than first for T0, T1, put this in a temporary register, and then do it a second time. And then you have to check that both are 0, right? To say that they are equal. Yeah. This might require 3 instructions, right? Because to check that both are 0, to return a 1, that's not really a trivial thing to do. Maybe you need actually a NOR instruction, but the NOR, okay, if you take the NOR of 0 and 0, you will get 1, right? Because the OR will give you 0. Yes. But NOR will give you all the bits to be 1s. You want exactly a 1. You don't really want all the bits to be 1. You don't really want to get 1, 1, 1, 1. If you use a NOR instruction and you need two registers which are both 0s, it might not work to use a NOR instruction. So the NOR is not a solution. You have to use a branch, maybe, right?
I thought about using the add instruction. If I get one, I add the result of the 2 first statements with
So if
1.
you get 0 and 0, you add them, you get 0. If you add actually 0 and 1, okay, and then what?
If I get 1, then they are equal. If I get more than 1, they are not equal.
I have an idea.
No. Well, let us see someone else. Okay, so you said that actually if T0 is not less than T1 and T1 is not less than T0, then they are equal. So when you add them, you either get actually 0, 0, you get the result is 0, then they are equal. True?
I add them with 1 because I want the result of equality to be 1.
So if you add them directly, you either get 0 or 1.
Yeah, then I add them again with 1. If I
you get 1 or 2.
Yeah, if I get 1, they are equal. If I get 2, they are not equal.
But I really would like to get the result in T2 to be 0 or 1. Because set if equal, the result is true or false, right? So true is 1, false is 0. It's not 2. Yani what I want at the end, the value of T2 to be 0 or 1. That's it. Any other idea? Can someone suggest other than Khalid?
Yes, maybe we can use XOR bitwise. Then the result we use set less than immediate or compare it to 0. Then if the result is
so if you XOR them, yeah, okay. So let me just understand what you are saying. So you want to XOR T0 with T1, right? Yes. And if you XOR them and they are equal, you get 0. Exactly. But if you XOR them and they are not equal, you get any result which is different from 0.
Yes.
Okay, good. So we can XOR first, and then what will be the second instruction?
Set less than immediate, where we take the result of this XOR and we use it as Rx, and we set immediate value 0. if this RS less than 0 is mean if RS is equal, mean RS 0, that means RS is less than 0 would be wrong. Then the RT, the value in RT is 0. That means they are equal. If the RT is other than 0, that means they are not equal.
So if you are checking if it is set less than, so I'm going to use set less than immediate, right? And you would like to suppose that the XOR, we place the result in some temporary register, let us say T3 or any other register, right? So you would like to check the value of T3 after XORing. So you XOR T0 with T1, you place the result, let us say, in T3, and then you would like to check, okay, if the result in T3 is set less than immediate, so you would like to check if it is less than 0.
Sorry. So I have to check if it's again same instruction. Maybe it's gonna be more than one instruction, more than two instructions. I have to check if it's less than 0 or greater than 0.
So if it is less than 0, it means negative.
Yes.
But how is this related to being actually equal or not equal? Because they may not be equal and it's not negative when you XOR them. Maybe the most significant bits are identical, but the remaining bits are different. So therefore, the result is not negative. So when you XOR, you can actually get any result. When you XOR two registers, you can actually get any result, positive, negative, 0. 0, it means that they are equal. But when you XOR, you might actually get also positive or negative, right?
Yes.
So yeah, you can XOR, but the second instruction is you have to be careful about the next instruction after XORing. طيب, anyone else would like to suggest a solution to this? We did not solve it yet. Okay, set less than immediate was very close, but you have to be careful about how to use this instruction. Anyone else? Anyone else would like to suggest a solution for this problem? Equivalent MIPS instruction. It can be done in two instructions. Okay, let me show you the solution. So the first instruction will be, let us say, XOR or subtract. Either one is fine. I'm writing subtract here. So basically, we can subtract. We can calculate T0 minus T1 and place the result in some register T2. Now I'm placing the result in T2 because I would like to write to T2. Okay, this is my destination. So I don't really want to use any other register. Okay, so I'm going to use T2. And I'm going to use set less than immediate unsigned. Now, there is a difference between set less than immediate and set less than immediate unsigned. I would like to check if T2 is less than 1. Okay. Now, let us understand this second instruction. When you subtract, you get the result in T2. If T0 and T1 are equal, you get 0. Right? If T0 and T1 are equal, you get 0. But if T0 and T1 are not equal, you actually can get any value in T2. Now, you would like to look at the value in T2 to be unsigned. So if it is 0, it will be less than 1, and therefore the result will be true. But if it is a result which is anything different from 0, positive or negative, you treat it as unsigned. Then therefore it would not be less than 1. It can be 1 or a greater. So therefore it will be false. So in other words, if the result in T2 is 0, then they are equal. Then the set less than immediate unsigned will find that 0 is less than 1. So put 1 in T2. So change it from 0 to 1. The set less than immediate unsigned. And if the value of T2 is any other value other than 0, then it would not be less than 1. Okay, it can be greater than or equal to 1. Okay, the unsigned value of T2, then place 0 in T2. So if any value in T2 is different from 0, it will write 1 into T2. Okay, so it will write, if it is any value which is different from 0, it's going to write 0 into T2. It will be false. If it is 0, it's going to write 1 into T2. We could have chosen here a different register other than T2, but the idea is that we don't really want to modify any other register because this is a pseudo instruction. So a pseudo instruction is not really supposed to modify any other register other than the one which is the destination register. Okay. But in the MIPS architecture, they use one other temporary register, which is called the assembler temporary. I'll talk about it in a minute. Okay, so this is really the idea of using set less than immediate unsigned. Okay, so it's a careful translation of the set if equal. So subtraction will check if the result is 0 or not 0. We place the result in T2. If the result is 0, we get 1 in T2. If the result is different from 0, any other value, okay, then in this case we get 0 in T2 because it would not be less than 1. It will be greater than or equal to 1. 1, you look at the value to be unsigned. Okay. Right. So we see that we can take any one of these pseudo instructions and we can find equivalent MIPS instructions, but we have to translate it carefully. Now we can have pseudo branch instructions. So in the previous slide, we have seen, pseudo compare instructions. We can also have pseudo branch instructions. So we have branch if equal, branch not equal. These are real branch instructions, but we can also have branch less than unsigned, branch less than or equal unsigned, and so on. So we can define all of these eight branches as a pseudo branch instructions because they are not defined in the architecture. So let us take a look at the first one, branch less than. How do I translate branch less than into equivalent MIPS instructions? So branch less than is not defined by the MIPS architecture. There is no implementation for it. So how can we have equivalent MIPS instructions, for a branch less than? It's defined as a pseudo instruction in the assembler. So how does the assembler translate? How does it translate the branch less than into equivalent MIPS instructions? Students, are you with me? I need an answer. Let me ask Salman. Salman, give me an answer. Salman, are you with me?
Yes.
Okay, so tell me how branch less than can be translated by the assembler into equivalent MIPS instructions. If you don't know, you can just say don't know.
Don't know.
Omar?
Yes.
Okay, tell me how to translate the branch less than into equivalent MIPS instructions.
We'll have to use the SLT, which is comparison.
Yes. So we can compare T0 with T1, but set less than will be true or false. And then?
I think we have to use one of the original branch instructions.
Yes. So we branch if what? If the result of the comparison is what? It's true. We branch
Yes.
if the result of the comparison is true. So branch if it is equal to 1. So what we have to do is that we have to use set less than to compare T0 with T1. We place the result in a temporary register. Okay, so this is shown here. So we use set less than to compare T0 with T1. Let us place the result in the assembler temporary register AT. Now AT here is a temporary register used by the assembler specifically for translating pseudo instructions into equivalent MIPS instructions. And the reason why the assembler uses this register to avoid using any register which is used by the programmer. So sometimes for some pseudo instructions, the assembler needs an extra register. And this extra register is the assembler temporary. It requires a temporary register. So the assembler uses this assembler temporary. It is reserved for the assembler to use it to translate pseudo instructions into equivalent MIPS instructions. Okay, so the programmer should not use the assembler temporary because it is reserved by the assembler for translating pseudo instructions into equivalent MIPS. Now, set less than is going to write true or false. So if T0 is less than T1, it's going to write 1. If it is false, it's going to write 0. Okay. Now, what we need to do is that we need to branch. We need to branch if the value in AT is 1. So we use a branch not equal, and we compare the register AT against 0. So if it's not equal to 0, it must be equal to 1. Because set less than is going to write only 1. It's going to write either 1 or 0. So there are only 2 possible values that are written in AT by the set less than instruction. So if it is not equal to 0, it means it is true, it is 1, we branch. If it is equal to 0, if set less than writes 0, we are not going to branch. So the branch will not be taken. Okay? So by using the sequence of instructions, set less than followed by a branch not equal, we have now a new pseudo instruction, which is branch less than. So this sequence is equivalent to branch less than. So there is no real instruction which is branch less than. It is defined as a pseudo instruction, and the assembler translated into a sequence of 2 instructions. So this is the translation of branch less than. Set less than and the branch not equal are basic instructions which are implemented in the hardware. Okay. How about branch less than unsigned? The second one here.
It is the same, but he use different I think it should be branch if equal.
No. If we have here branch less than unsigned, let me just use my pen tool. Okay, let me just turn off my camera. So if I use here branch less than unsigned, let me just write here unsigned. Okay, all what you have to do is just use set less than unsigned. That's it. This is how you fix it. Okay, so if you have branch less than unsigned, use set less than unsigned. How about the branch less than or equal? I would like to branch.
I thought you meant the less than or equal.
Yeah, for less than or equal.
Yeah, it is the same.
I would like to branch.
You use.
Yeah. So
okay.
What do we use?
We use branch equal.
Well, to say that T0 is less than or equal to T1, let me write it down. T0 is less than or equal to T1. I would like to branch if T0 is less than or equal to T1. That's the meaning of branch less than or equal. Okay? So what I have to do is that I have to say that T0 here is not greater than T1. You agree? Because the meaning of less than or equal, it means not greater than. Okay? So not greater than is less than or equal. And to say that T0 is greater than not, okay, T0 greater than T1, it's the same thing as saying that not here. Let me write it down. T1 is less than T0. So switch the order of T0 and T1. So now I have to compare T1 with T0 using the set less than. And if this is true, now notice that I would like to branch if not T1 is less than T0. So this is equivalent to this. They are equivalent, right? So I'm going to use here set less than to compare T1 with T0. Notice the order here of T1 and T0. Okay, so T1 here appears before T0. Okay. So I would like to check if T1 is less than T0. And then we can say branch if equal. So we would like to branch if it is equal to 0. It means then the branch if it is false. This is why we have this not here. So I would like to branch if this is false. Do not branch if it is true. So you see that we can achieve any one of these branches, okay? So even though I don't really have set less than or equal, I have set less than, we can always convert less than or equal to not greater than, and I can switch the order of these two registers, T1 and T0, to make that T1, so to say that T0 is greater than T1 is the same thing as T1 is less than T0. So I can actually, I use set less than here to compare T1 with T0. And then I use branch if it is equal to 0, branch if it is false, because I really want to branch if it is not less than, okay? So we branch if it is equal to 0, we branch to label. Okay, is this clear? So these actually, you have to understand the logic behind so the meaning of these pseudo instructions, and therefore you can always take any one of these, okay, any one of these 8. Of course, the first 4 are used here for signed integers. The next 4 are used for unsigned integers. So we can always define these branch instructions in the assembler without the need to define them in the hardware. Okay, so it's enough to have the set less than, branch if equal, and branch not equal to implement any one of these branches. So we can have always a sequence of 2 instructions for any one of these branch pseudo instructions. Now notice that here AT, I used AT. AT is defined as register 1. Okay, let me just clean up here my slide. Okay, let me erase all the ink. So I used here the AT register. Okay, in all of these pseudo instructions, you are allowed okay, to use the AT register. So AT here is register number 1, and this register is called the assembler temporary register. Okay, it's called the assembler. So AT stands for assembler temporary. It's used by the assembler to translate pseudo instructions into equivalent MIPS instructions. And the reason why the assembler uses AT to avoid using any other temporary register which can be used by the programmer. So remember that the translation from pseudo to equivalent MIPS should not modify any register except the assembler temporary. Okay. So the assembler temporary can be used by the assembler to translate pseudo branch instructions to avoid modifying any other temporary register. Now we can use these pseudo branch instructions in programming. Okay, so now once we have defined them in the assembler, now it becomes very convenient to translate if statements using the pseudo branch instructions. Let us take a look at the first example. I would like to say that if T1 is less than or equal to T2, then execute this instruction. So how do I translate this? How do I translate this? Yes, Mustafa.
Set if less than equal. I use the.
There is no set less than or equal. I can use the branch.
You can use a branch if it's greater than.
Can you hold for a second? Just for 1 second. I have somebody actually knocking on my door. Okay, give me 1 minute. I'll come back to you. Okay, just please hold. هيدا مرة وتقول أنا أخاف نفسي يكتب محاضرة أونلاين لكن تقال أغلبها من هذا افتح الكتاب. Okay, sorry about this. Let me continue. So now let us take a look at the if statement. Okay, are you still with me?
Yes.
Okay. Now, how do we translate the first if statement?
Branch if okay, I can use greater because it's less than equal is not greater.
Exactly. So we can branch if the condition is false. I can
Yes,
branch
I can
outside
branch.
the statement. So the idea of branching is to skip. Right?
Yes. So
I
I
really
use
would like to skip. I would like to skip the if statement if it is not less than or equal. What is not less than or equal?
greater. Branch
Exactly.
greater.
Yes.
Then okay, move.
So we can actually branch here to L1, and then here T3 becomes T4. We just copy it. So the move instruction can copy the value of register T4 into register T3. So T3 becomes T4. Now notice it says that the value of T1 and T2 are unsigned integers. It says unsigned very clearly. So for this reason, I have to use a branch greater than unsigned. Okay? So it's a branch greater than unsigned because it says they are actually unsigned integers. So for this reason, we have to use a branch greater than unsigned. Is this clear?
Yes.
Clear.
Type. Remember that the branch greater than unsigned is not a real instruction. It's a pseudo instruction. And therefore, it's translated by the assembler, okay, into real instructions, into MIPS instructions. So really, this branch greater than unsigned is translated into two real instructions by the assembler. Move also is a pseudo instruction, which is translated into one real instruction by the assembler. Okay? And for example, it can add register T4 to register 0 and place the result in T3. So these are pseudo instructions, but you can use them as if they were real instructions and leave the translation to the assembler. How about the second one? If T3 less than or equal to T4 and T4 is greater than or equal to T5, then T3 becomes T4 plus T5. How do I translate this?
Since
Notice
we have,
that there is a logical and here.
Yeah, since we have and remember in the lab we have to do something like circuit something. We
Short
list.
yeah,
Yeah.
It's called short circuit evaluation. Yes.
So we only branch if one of the two is false.
So start with the first one.
Yes.
If the first one is false, and anything is false, skip the entire if statement.
Yes.
Okay, so what's the condition here for false?
Less than or equal.
What is not less than or equal?
Branch if greater than.
Yes, but it says that they are signed. So we should actually make sure that we use the correct branch instruction. Okay,
Yes.
so we have to be actually here a branch greater than.
Yes.
T3, T4, where do I branch? I have to branch outside the if statement. Okay, so I have to use like a label here. Okay, so this label here has to be outside after the if statement. Right. What should be the next instruction?
Branch less than.
Exactly, strictly less than. T4, T5, again outside. And if I don't branch and I don't branch, it means this is true, this is true. So therefore we write an add instruction for adding T4 plus T5. Good. So notice that we have used here a branch greater than, because a greater than is not less than or equal. To skip here, so notice that I'm branching outside the if statement. So this label L1 is outside. Here I use the branch less than, which is not, okay, less than or equal. So if this is false, we branch outside, and then we add here T4 plus T5 and place the result in T3. So it's all about logic here and understanding how to use the correct branch instructions, okay, properly to translate the Boolean expressions that exist inside the if statement. Okay. Notice that branch greater than and branch less than. Well, okay, these are pseudo instructions, right? So they use the set less than and branch if equal or branch not equal to translate these instructions, but we will not really worry about them. So each one of these two, branch greater than and the branch less than, these two are pseudo instructions. And therefore, each one of them is translated into two MIPS instructions, as we have seen in the previous slide. Okay? Right, let me move to another topic now. So this is basically how we use pseudo branch instructions to translate if statements. Let me talk about the conditional move instruction. So MIPS also defines, in addition to the branch instructions, it defines, and also the compare instructions, it defines something which is called conditional move instruction. So we have move if 0 and move here if not 0. Move n means not 0. Okay? So the first instruction, what it does, we call this conditional move. Okay, so the first instruction, what it does is that it's going to check the value of register RT. If the value of RT is equal to 0, it will copy RS into RD. Okay, so basically it's going to move the value of RS into RT, but conditionally, if the value of RT is equal to 0. If the value of RT is different from 0, move Z will not really move anything. Okay, it will not move. In the case of the second instruction, move if not 0, it will move if the value of RT is different from 0. So the first instruction is going to move if the value of RT is 0, and the second one is going to move if the value of RT is different from 0. It simply copies the value of RS into RD. Both instructions are of the R type. You can see the opcode is equal to 0. And you can see they have unique function codes and 3 registers, RS, RT, and RD. So we check the value of RT if it is 0 or different from 0, and we copy the source register RS into destination register RD. So this is the definition of these conditional move instructions. It turns out that conditional move are really very, very useful, okay, for translating if statements. So without the need of using branch instructions. So let us take a look at this if statement. If it says if T0 is equal to 0, then T1 becomes T2 plus T3, else T1 is equal to T2 minus T3. Of course, I can translate it with the branch instructions. I can use a branch and a jump to skip the else part. For example, I can translate this if statement here using a branch. I can say that branch, if it is not equal, if it is not T0 is not equal to register 0, which is 0. So branch if T0 is not equal to 0, branch to L1. So branch to the else part. So here L1, it's a label for the else. Do the subtraction. T1 is equal to T2 minus T3. But if we don't branch, it means that it is equal to 0. Then we do the addition. We do the if part. So we add here T2 plus T3. We place the result in T1. But when we add, we also have to skip the else part because we don't really want to add and subtract at the same time. So this is why we jump here to L2. This is done after the addition so that we skip the else part and we jump outside the if statement after the else part. So notice that we have used a branch and we have used a jump to translate the if statement. But we can do it differently with the conditional move instruction. Using a conditional move, we can avoid using branch. We don't really need the branch and the jump in this example. So what we can do is that we can do the addition anyways. Do the addition, add here, okay, so T1, T2, T3, do this addition, regardless of the value of T0. Okay, do the subtraction, place the result in any other register other than T1. So do the addition, assuming that T0 is equal to 0. Do the subtraction also anyways, place the result in some other temporary register other than T1, and move the value, for example, place it in T4, and then move the value of T4 to T1 if the value of T0 is not equal to 0. That's the meaning of the else part. So if it's equal to 0, already we have done the addition. If it's not equal to 0, then copy the value of this subtraction into T1. So this is translated like this. So first add, okay, place the result in T1. So we place the result in T1 assuming that this condition is true. Okay, and then do the subtraction, but don't place the result in T1. Use any other register, for example, T4. Okay, so we have done the addition, we have done the subtraction. So we have done the if part as well as the else part. And now move the value of T4 into T1 based on T0. So we copy the value of T4 into T1. So the result of this subtraction here, that we have it in T4, move it into T1. If the value of T0 here, the value of this T0 is what? It's not equal to 0. So we use move n here. So if it's not equal to 0, we should execute the subtraction, and therefore we copy the value of T4 into T1. So we avoided using any branch and any jump, and we have replaced them with just with the conditional move. You understand the logic behind this?
Yes.
So this is really, yes.
Doctor, I have a question. Which one is better? Is it to use more registers, or to use more number of commands or lines?
So we have reduced, okay, in this example, using the conditional move is better than using the branch and the jump. Okay, so rather than actually using the branching and the jump to skip instructions, we were able to do it with conditional move, and these instructions are executed in sequence. It's okay to use an extra register, like for example, T4. Okay, so this will not really cost us anything because these registers already exist in the hardware. So using an extra register is okay, but reducing the number of instructions, these can make the program to run faster. Okay, so the conditional move not only made we have eliminated the branch and the jump, but also makes the code to run faster. Okay, so we have 3 instructions rather than 4 instructions, and this code will be executed sequentially and faster without the need to skip instructions. So for example, this branch, if it is true, we're going to skip these 2 instructions and go to L1. This jump is going to skip the subtract instruction and go to L2. Okay, so this kind of coding here, to have too many branches and too many jumps, will cause the program to run slower. Okay, without eliminating the branches and the jumps is better. Okay. Any other question about the conditional move? So the conditional move here can eliminate the branch and the jump instructions.